So we are ready to start, I think. Good afternoon, everyone. My name is Gabriel Chiara. I'm an associate professor here at the University of Canterbury in geotechnical engineering. And today is my pleasure to present Mohammad Koopaee, which is going to give a presentation about 45-50 minutes probably as a part of his Ph.D. oral defense, which will happen just after this presentation. I think we don't have time to go through your bio, so without further ado, I will let Mohammad start his presentation.
Yeah, thanks very much, Gabriel. Good afternoon, everyone. Welcome to my presentation. The title of my presentation today is Simplified Seismic Collapse Probability Prediction for Loss Optimization Seismic Design. Sorry, Gabriel, I can't see mouse here, and I need mouse or pointer. Oh, I need to look at this one.
No, please.
Ah, yes, thank you. Yeah, thank you. So as a lot of you may already know, the experiences from the past recent earthquakes have identified that conforming to the seismic design requirements in modern seismic codes and guidelines have generally been successful in saving lives. However, still the consequences, the financial consequences of these earthquakes have been extensive. To address this issue within the past couple of decades, I would say the attention of the earthquake engineering community has been shifted from saving lives to minimizing the financial implications of seismic events. Several different performance-based procedures have been proposed in literature to estimate the losses, and in line with the momentum in development of seismic design procedures based on financial losses, a preliminary framework for loss optimization seismic design was first proposed in 2010, which happens to be the title of my research and this presentation today. LOSD, Loss Optimization Seismic Design, offers, at least aims to offer, a complete, comprehensive, and reliable loss-based design methodology. An overview of the different steps involved in LOSD are shown here in this figure. And as you can see by red, one of the major steps in LOSD is estimation of seismic losses, which is the topic of this PhD thesis and also my presentation today. With that introduction, there are 5 objectives for this research, which through my presentation I go through them one by one. It starts from development of an enhanced framework for LOSD, and it goes and eventually finishes by development of a simplified procedure for seismic collapse probability prediction of RC frame buildings. The last one is the main objective of the research, and some of the other objectives there are actually auxiliary objectives to reach to that final goal. I start with the first objective, which is development of enhanced framework for LOSD. In order to improve the framework of the LOSD, we have proposed conducting loss assessment for LOSD with 3 different levels of computational rigor or computational effort. That is to respond to the completeness and comprehensiveness of the LOSD procedure. The first level of computational rigor is rigorous LOSD, and the second one is semi-rigorous, and the last one is simplified LOSD. The framework for rigorous LOSD or rigorous loss assessment has been already defined and proposed in literature, and here we are proposing frameworks for semi-rigorous loss assessment and a simplified loss assessment procedure. Through an example of a case study building, I explained the differences between three different levels of computational rigor. But in summary, the first level, the rigorous loss assessment, is based on conducting nonlinear response history analysis. The second one is based on a nonlinear pushover analysis, and the simplest one is based on a simple linear equivalent static analysis. The other differences I explain as I go through an example. This is the case study building, which I'm going to use to explain different levels of computational rigor. And also the same case study building has been used in several different chapters of the thesis. It has also been used by several previous research. It is the well-known 10-story RC building in New Zealand Red Book, which acts as a design example for reinforced concrete buildings designed in accordance to New Zealand standards. I start with the rigorous LOSD. There are several different steps to conduct a rigorous loss assessment. I'm not going to go through all the steps because it's beyond the scope of my research. And more, I just want to go to the end results so that we can just compare different levels of computational effort. Through these steps that I've pointed out here, first a collapse fragility curve is generated. Collapse fragility curve shows the relationship between the probability of collapse at a given intensity measure with respect to intensity measure, which in this case has been selected as a spectral acceleration at the fundamental period of the building. That has been calculated using nonlinear response history analysis to be 11% for this case study building. Note this number because we're going to compare this number with the other two levels of computational rigor later. Following generation of collapse fragility curves and estimating probability of building collapse at different hazard levels, there are several other steps to go, and eventually what we get is a loss given intensity measure relationship or loss given intensity measure function, which shows the loss of the building at different intensity levels. This can be used to predict the loss at different hazard levels. For this example, I have shown the loss of the building at MCE, which has been calculated to be 28% of the total building loss. Again, note this number because we're going to compare it with the other levels of computational rigor. Now going to the semi-rigorous LOSD or semi-rigorous loss assessment. The semi-rigorous assessment in this procedure is based on conducting a nonlinear pushover analysis at a given hazard level. In contrast to the rigorous LOSD, it's an intensity-based assessment, meaning that we just undertake the loss assessment at a given intensity level. In this example, we have chosen MCE level. For the pushover analysis, we have recommended using the extended N2 method, which has been developed by Professor Pfeiffer and his team. We have recommended this procedure simply because it has been extensively verified. It has been developed through several years of research by the Professor Pfeiffer's team, but any other pushover analysis method also can be utilized in this framework. Here I have shown different steps involved in the pushover analysis using the N2 method. There's not enough time to go through all details of the steps, but what I can say is that through these steps and developing the pushover curve for the building, we can calculate the spectral acceleration capacity of the building. With the spectral acceleration demand obtained from a response spectrum, which can be the response spectrum in the building codes. We can also predict the spectral acceleration demand. The spectral acceleration demand can be transferred to spectral displacement demand, and from there, target displacement at MCE in this example can be calculated. Following that, at the target displacement level, from the pushover analysis, we can get the median values of inter-story drifts, and we can use the dispersion. This curve here just shows the inter-story drifts, which have been calculated with the N2 method, extended N2 method, and for comparison purposes, it has been also compared with a nonlinear response history analysis. Having the spectral acceleration demand and the spectral acceleration capacity in previous steps, using a log normal distribution with this equation, we can predict the probability of collapse at a given intensity level, which in this example is the probability of collapse at MCE. For this case study building for MCE, the probability of collapse obtained was 9%. In comparison to the 13% which was obtained from rigorous analysis, it's very close. Even though I showed more steps here, it's actually a lot easier to conduct in comparison to a nonlinear response history analysis. From here, again, I'll just go very briefly through the steps. We can develop the distribution of engineering demand parameters at different floor levels from the pushover analysis, and then going to the next step, which is the assessment of loss based on the engineering demand parameters or based on inter-story drifts and peak floor accelerations. We need generic graphs or functions to relate engineering demand parameters being inter-story drifts and peak floor acceleration to loss. An example of these functions are shown here, developed by others. From this graph, we can simply obtain the median loss at a given inter-story drift and at a given peak floor acceleration, and then we can have the distribution of the losses given intensity measure as well. And this can be done for various floor levels. Results of such analysis are shown here for different floor levels, and by summing up the loss of various levels, the total expected loss from all floor levels at MCE can be calculated. In this example, it has been calculated, 3.07 million. Having the total cost of the building, the final result, which is the loss at MCE, the expected loss at MCE is 22% of the total building cost. In comparison to the rigorous method, which was 28%, it is again fairly close. And in this method, you realize that we actually didn't need the complete inventory of all building components, because using the EDP loss function, generic functions, we remove the requirement of having the fragility functions for all different building components. Moving on to the most simple approach, as I noted before, it is simply based on a linear equivalent static analysis procedure. The results of such analysis for the case study building has been shown here. At this stage, we need to compute the probability of collapse at MCE level. For this purpose, we need an equation or a function or a graph or something, a tool, to calculate the probability of collapse from the results of this simple linear analysis. And that has been what has been addressed in this Ph.D. thesis. This equation that you see in front of you is the result of my research. I'm going to discuss about how this equation has been developed in detail throughout my presentation. However, just for the sake of this example, it was shown that it's predicted to be 13%. The value is very close to the rigorous analysis. In comparison to the rigorous analysis, this is a lot simpler to get. It's actually really simple. So this is the main purpose of the thesis. Having the linear responses of the building, we can also calculate the interstory drifts, and using the EDP loss functions, we can calculate the loss at each story level. Again, this exercise has been done, and eventually the loss of the building at MCE level has been estimated to be 29% for this particular example. So again, this value is very close to what we got from the nonlinear response history analysis. This is just an example. We are not necessarily saying that the results that we got here is completely correct, because it's ongoing research to fill several gaps that are still existing. However, I believe that even with the existing knowledge, we can get very good results using this simple framework. Now, if I want to just list key contributions of this part of the research, the first one is that we have proposed different levels of computational effort or rigor for LOSD, so that we have extended the framework of the LOSD, and now we have introduced LOSD as a comprehensive procedure, which can be used not only for as a quick method, but also for different buildings with different importance. And also the framework for a pushover-based seismic loss assessment has been proposed. From here, the attention or the focus of the research is shifted to prediction of probability of building collapse. Again, I've just summarized the steps in the loss assessment, and as you can see here, prediction of building probability of building collapse is an important step, as you could also see in that example. The purpose here is to develop a simplified equation for prediction of probability of collapse of buildings at a given hazard level. In order to reach to that objective, we have adopted this research methodology that I've listed here. The first step, we have decided to undertake a vast number of rigorous collapse analysis using nonlinear response history analysis method on a vast number of cases to the buildings with varying heights, number of bays, design drifts, and structure detailing. Using that, we can actually identify the key parameters that affect seismic collapse capacity of RC frame buildings. Knowing those parameters, we can simply fit the data to an equation, and once the equation is developed, we can verify the equation for buildings which are outside the range of our case study buildings, which we actually use to develop that equation. I'm just going to go through all these steps of our research methodology one by one, starting from the first one. So, in order to undertake rigorous collapse analysis, there are three aspects in the probability of building collapse estimation which needs to be thought about. The first aspect is structural modeling, the second aspect is ground motion selection, and the third one is prediction of uncertainties. The first and the second one have been addressed and have been investigated in this thesis, and the last one is just outside the scope of this work. I start with the structural modeling for collapse simulation. In order to develop or use the structural model for collapse simulation, we need to understand first the modes of the structural collapse. generally, the collapse modes of building have been classified in two categories in literature: sideways mode of collapse and vertical mode of collapse. Sideways mode of collapse is as a result of the reduction of load carrying capacity of structural components due to excessive P delta effects accelerated by degrading behavior of structural components, which eventually overcome the gravity load carrying capacity of the building. It happens typically for ductile buildings, and it happens in really large or very large interstory drifts. The second mode of collapse is the result of direct loss of gravity load carrying capacity in one or several structural components. It doesn't necessarily happen in large interstory drifts, and it mostly happens in non-ductile buildings. But in some cases, as I'm going to show, it may also happen in more ductile detail buildings. Majority of research in the literature have been concentrated on modeling or simulating the sideways mode of collapse using lump plasticity models. For that reason, I'm just going to go focus a little bit on the vertical mode of collapse, which we also going to take into account in this research. These are some of the examples of vertical collapse. One thing that I need to add is that with the sideways mode of collapse, we see complete crushing of the building. There's nothing left on the building, and the building completely collapsed normally. Whereas with the vertical collapse, we might have the collapse or failure of some components. And if those components are important components, for example, like this column in this building, that is resulted in complete damage of the building, and the building is not repairable after the earthquake, and we will probably also have some injuries or maybe death. The photo on the right shows another example of vertical collapse, just to show that vertical collapse can be complete failure, or it can be partial failure of the building as well. Moving on to more modern recent buildings, this photo on the left shows the VNZ building in Wellington. It's been designed as a ductile building. Due to as you know, the building has been now demolished. The floors have fallen down due to the elongation of the beams. So it's still vertical collapse may also happen in some more recent modern buildings. The other example are these two buildings in 2020 earthquake in Turkey. Both of the buildings shown here, they were not repairable, and they were not used anymore after the earthquake. One failed because of the failure of the columns, and the other one was just badly damaged again because of the loss of the load carrying capacity of the columns. So, as I noted, majority of research has been on the simulation of sideways mode of collapse with lump plasticity models, similar to what I've shown here. For this, several different models have been developed, which they can capture the stiffness and strength degradation of structural components, which is important to capture for simulation of the sideways mode of collapse. There are some shortcomings in the lump plasticity models. The first one is that vertical modes of collapse cannot be directly predicted in the model. As you can see in this example of the IDA, it's been shown by Neil that the sideways mode of collapse has been captured by this model, but the vertical collapse has actually occurred prior to the sideways mode of collapse, in this case for a non-ductile structure, and directly the vertical collapse cannot be captured. Indirectly, there are methods proposed in the literature and that they can actually capture this. The second issue with the lump plasticity models is that the flexural-axial interaction of our RC columns is typically ignored. In the other words, variation of the axial forces in columns during analysis is not captured. This is an issue that I'm going to talk about it more in my next slides. And the third issue is elongation of the structural components is not simulated. As you saw in one of the photos, that building was actually collapsed. The floors were collapsed due to elongation. If that building was modeled using the plastic hinge model, that could not be captured. So that is an issue here. And the fourth one, which has been noted by some research, is that these models are greatly sensitive to the parameters, and especially for the collapse prediction, if you use different parameters, you're going to get different results. So we are looking for a structural model that can directly, this was actually our purpose during the research, it can directly not only estimate the sideways mode of collapse, but also the vertical mode of collapse. To that purpose, we did a little research and literature review, and we realized that we can actually adopt fiber element modeling technique to simulate both modes of collapse. The accuracy of fiber element model depends heavily on the adoption of the material models which can be used in the analysis. So we need some material models that can capture strength and stiffness degradation of the structural components, and also they can capture the fracture of reinforcing bars and crushing of concrete. If we do have those material models, then we can model. We can model both vertical mode of collapse as well as the sideways mode of collapse. These material models are available in the literature. So what we did in our research was that we simply used these material models in a fiber element modeling technique, and by using those, we can capture both sideways and vertical modes of collapse. These material models that have been used for this research, I'm going to go through them with more details later, but not at this stage. At this point, I just want to show the ability of the material model to capture loss of vertical load carrying capacity. This is an example of a cantilever column under cyclic loading, which was analyzed, and this shows the stress-strain diagrams at the failure point. If you look at the stress-strain diagram for the concrete, for this section, the section of this column on the left and right, you can see that on both sides, the concrete has been under tension, meaning that the cracks have not actually closed, and they've been still open. So the whole section has been under, in fact, the whole compression has been taken by the reinforcing bars, and in this particular example, eventually failure has happened due to the low cycle fracture of the reinforcing bar. This is throughout the analysis in prediction of the structural response. As I noted, one of the advantages of this model is that we can actually capture the axial load variation. This is a symmetric portal frame under cyclic loading. If you follow the blue lines, you can see that the response of the column on the left and the column on the right has not been exactly the same throughout the analysis, and that is due to the variation of axial forces throughout the analysis. If we were to model this with a lump plasticity model, we would simply just use a single value for the axial forces. The purpose here is not really to say which model is more accurate. The purpose is more to show that with the model that we have adopted, we can capture these effects. In particular, in this slide, the effect of variation of the axial forces throughout the structural analysis. These two curves again are showing the moment curvature and axial load deflection variation between the two columns of that symmetric corner frame. We can see that throughout the analysis that has varied, and that has been captured by the structural model. The key contribution in this part of the research has been we haven't proposed a new structural model. We have simply used the models existing in the literature, which have been extensively verified through experiments, and we have shown application of a fiber element modeling technique, particularly for simulation of collapse, both sideways mode of collapse and also vertical collapse. So in fact, we have also included vertical mode of collapse in the structural model. Going to the next step of the research, in order to generate collapse fragility curves, we need, there are two approaches to generate collapse fragility curves. The first approach is the ideal curve traditionally, and the second approach is what is called multiple stripe analysis. Multiple stripe analysis is nonlinear analysis at different steps, and in those different steps, we need a ground motion selection method. So the question here is that what ground motion selection method we should use for our analysis, and if we use a particular ground motion selection method, what is the difference between this method to if we had used another method? So to get the answer, we have conducted extensive analysis through a case study building. We have adopted the case study building of the New Zealand Redwood building, and we have conducted collapse analysis with 3 different ground motion selection methods: uniform hazard spectrum, conditional mean spectrum, and the GCIM method. For the uniform hazard spectrum method, we use 2 procedures from probabilistic seismic hazard analysis and also from simply New Zealand code. And so there are several aspects in ground motion selection, which I'm not going to go through all details of them. But one thing that we needed to decide was what period of range, because 2 out of the 3, or if we count these as 2, 3 out of 4 methods here, they used a target spectrum and then they matched the ground motions to that target spectrum. What period range we should use to match the ground motions? We used 90%, the period with 90% mass participation factor for the lower bound. For the upper bound, the upper limit of the scaling period range should correspond to maximum post-yield inelastic response of the structure. So we have in fact proposed this equation for the upper bound of the ground motion selection. In order to construct the collapse fragility curves based on multiple stripe analysis, we get the collapse probability data points, and we need to fit a curve to those data points. We have developed and proposed a novel procedure based on probability papers in here. It's a very simple procedure, and again, I don't go through the details of it, but it has been compared with one of the methods which is a lot more cumbersome in the literature, and we have seen very close results. The point here is that because we are conducting analysis at several intensity levels, we don't want to conduct analysis all the way until we get 100% collapse probability. So we need to actually predict the curve from some point, and that's where these fitting procedures become important. The other issue that we were facing was that those ground motion selection methods are conditioned on a given intensity measure. That intensity measure heavily depends on the structure period. The estimation of the structure period itself is controversial. There are several papers and methods to predict structure period, and also throughout analysis, especially for a collapse analysis, the structure period varies as the building moves into the nonlinear range. So the other aspect that we wanted to see was what is the effect of the structure period selection on the collapse probabilities. So here I've just moved on to the results for the case study building. We used period of 1 second, and also later we used period of 1.5 seconds. You can see the results, and then these results were fitted to a log normal distribution. In summary, what we observed here was that this is not probably the best period selection because it was the elastic period of the building. So now the results for period of the structure, then we assume the cracked section or cracked stiffness of the structural components. What we observed here, I just summarized the results. What you see here in this figure, first of all, is the result of 1,600 nonlinear response history analysis. And it's a fiber, it's nonlinear analysis through fiber malware. So each analysis has been taken between 4 hours to 24 hours time. So you can estimate how much time has taken to actually achieve this. What has told us eventually is that those ground motion selection methods which are conditioned on a given intensity measure are heavily reliant or dependent on the selection of a structure period. The results vary completely if you select different structure period. For the uniform hazard method, they are still different, but the difference is not as much as those the other methods. And the other result that we got, which you can better see here, was that uniform hazard spectrum method is conservatively or over-conservatively estimating the collapse probabilities by up to 40%. In order to compare the results for structures with different period, we have also proposed a new intensity measure, and that is return period, which enables actually a comparison of the collapse probability between different structures with different structure periods. So this table shows eventually the results of collapse probability assessment for the cases study building at MCE level. I'm just going to come back to this table later in my presentation, and collapse probability curves were also shown. So several key contributions in this chapter. I'm not going to repeat them, but it helped us to move on to the next step. We understood that because we are using a large amount of case study buildings, and we want to come up with an equation for simplified collapse assessment, and we probably want to be on the conservative side because we are aiming for engineering purposes. So we chose uniform hazard spectrum analysis, uniform hazard spectrum for the ground motion selection method. Now, going to the next step, as I noted before, now we are ready. We've got the structural model. We are well aware of the ground motion selection methods and what effects it's going to have on our end results. So we can move on to conduct rigorous collapse analysis methods on several case study buildings. So we started with a 4-story, 4-bay, 10-story building. designed with MUMO4 as per requirements of 3101. We call this the base building, and to just push the design to the limits of the code. One thing that I have to note here is that we actually it's a symmetric building, so we could use equivalent static analysis. We used response spectrum analysis, which is still allowed in the code. Because we got the base shear less than equivalent static procedure, so we scaled it up to 80% of the static equivalent static procedure, just to push the design to the limits of the code, and we limited the interstory drifts to the maximum allowed in the code to 2.5, which is 2.5%, and in New Zealand code drifts are simply calculated using this equation. Now, again, coming back to the structural model, I'm just going to quickly explain a bit more about the material models that we adopted, because that is going to have a significant impact on our results. So the material model that we adopted for analysis was the model developed by Kunas, proposed by Kunas. It has been extensively verified through experiments, so we don't need to verify the model again, because it's not a new model, it's been there, and we are just adopting it. So it captures the cyclic degradation and fracture of the bars with a low cycle fatigue model, and for buckling of reinforcing materials, it uses Dakal and Koopae's model, which is widely accepted in the literature. It has both takes into account both cyclic degradation and also failure of the bars due to buckling. A very important parameter in the buckling model of Dakal and Koopae is a parameter which we have called it LSR. LSR, as you can see here, is the ratio between the unsupported or buckling lengths of the steel bars to the diameter of the bars. So, what Dakal and his team, Professor Dakal, who is present in the room, and his team actually found in their experiment was that the unsupported lengths of the longitudinal bars is not only about the spacing between the stirrups, it is also about the relative stiffness between the longitudinal bars and ties. So, based on the experiments, assumption that buckling lengths of longitudinal bars inside an RC member is equal to the spacing of lateral ties is not always true. It's only true if lateral ties are sufficiently stiff, longitudinal reinforcing bars are slender, and tie spacing is actually large. They have developed a procedure to calculate what is the actual buckling or unsupported length of the reinforcing bars. It's not always the spacing between the bars. This issue has not been taken into account in our current codes. For example, if you want to detail this section, which is shown here, based on current requirements of 3101, we can use different alternatives which all satisfy the requirements of the code. But we get different buckling lengths, and with a larger buckling length, which is a larger LSR, the response completely is different. So this also hasn't been, at least to the best of my knowledge, hasn't been taken into account in the plastic hinge models which are developed in literature. So say for example, in this example I have shown, if you select the parameters for a plastic hinge model with different detailing, like the ones shown here, you get same parameters. And you get the same response. Whereas if you go with different LSRs and with the fiber model, you get quite different results, and that is because, well, in fact, longitudinal bars are going to buckle because the unsupported length is more than what you think they are. So, for the case study buildings, we investigated the effects of LSR on the collapse probability, and also we investigated the effects of the maximum design interest or drifts as two important parameters in the seismic collapse probability. So in here, you can see results of around 700 nonlinear response history analysis for the case study buildings, starting from the base model, which I explained, designed relatively to New Zealand standards. You can see the drift is slightly exceeds at 2.5%, but that is because it's been scaled down with the response spectrum analysis. And you can see the collapse probabilities with different LSR at 500-year return period. Typically for well-detailed buildings, the collapse probability is zero at 500-year return period. Most of the engineers in New Zealand, they are designing building, they are actually within this range, so number 3. So we get with good detailing zero collapse probability at 500-year return period. And then we continued the analysis at MCE level with a lot more case study buildings with different number of days, different heights, and you can see that we wanted to investigate two parameters. One was the effect of LSR, the other one was the effect of the interstory drifts. So as you can see, with the larger LSR, the collapse probability goes really high, and as we reduce the design interstory drift, the collapse probability becomes less. But what we observed was that the maximum allowed interstory drifts in NZ 1170.5 still may result in pretty high collapse probabilities if the design is pushed to the ultimate allowed limit. So just to see only the effects of interstory drifts, you can see the results for different LSRs. You can see that you can probably draw a line here that even with a very good detailing, if you've got good detailing, which means LSR equal to 5, with increased interstory drifts or design interstory drifts, we have converted the elastic ones to plastic. Still the collapse probability increases significantly. To investigate the effect of anti-buckling detailing, or in other words, that LSR, this shows the ratio of the increase of the collapse probability in comparison to LSR equal to 5 for LSR equal to 10 and 7.5. It is very important to see that this is like pretty much a straight line, meaning that if we go with higher LSR, like with different drifts, the collapse probability is going to increase by pretty much a single value. From these results, there we go. We obtained this equation which can give us the probability of collapse of buildings at MCE level given LSR of 5, because we just fit this equation to results of LSR of 5. You can see the comparison of the equation to the actual numbers. We extended this equation to 4 buildings with LSR over 5, and you can see the predictions of the equation in comparison to actual numbers for different levels of LSR. we need to verify also the procedure for a case study building outside the case study range that we used to develop the equation, and we went back to the Red Book building. In previous chapters, we have conducted nonlinear analysis for collapse probabilities, and then for this building, we calculated the collapse probability using the proposed equation, and we got 13%. If you compare this number with this column here, you see that it is conservative, expected. We wanted it to be conservative, but it is fairly close to the results of the uniform hazard spectrum ground motion selection methods. I'm just going to skip this and go back to the. So now we've got this simplified equation to predict collapse probability. If we rewrite that equation from a target probability of collapse, we can actually get a allowable interstellar drift, plastic interstellar drift. And that plastic, from there, we can actually calculate the allowable elastic interstellar drift. So using these two equations, we have proposed a very simple design method for reinforced concrete structures. It's very simple, and it's performance-based. It is probabilistic. I believe it fulfills all the requirements. With this procedure shown here, if you design a building with bad detailing, you're not going to achieve this allowable interstellar drift. Because your LSR becomes high. And if you design your building which is not stiff enough, then again you're not going to satisfy it because simply your drifts are high. So we believe we have addressed the issues, and here we go. We've got a simple, probabilistic, performance-based design procedure for reinforced concrete structures. We have made some design recommendations also. As I noted, we realized that LSR should be considered rather than just the spacing of the stirrups. Design interstellar drifts in 1170.5 are the maximum allowable is pretty high, and we suggest that it is prudent to detail the plastic hinge regions to LSR5. A procedure for designing sections to achieve LSR5 have been proposed here by Professor Dakal and his team, which combined with this procedure can provide a full methodology for design of reinforced concrete structures. Eventually, that was the purpose of this thesis. So we have been able to quantify the effect of design interstellar drifts on seismic collapse probability. We have quantified the effect of anti-buckling detailing. We have developed an equation for simplified collapse prediction. We have developed a new performance-based procedure for design of RC frame buildings. Thank you very much for being here and listening to my presentation.
Disconnect her now. Yeah.
Thank you, Mohammad, for a very comprehensive and informative presentation. Now, before opening the room for audience, the questions, I need to ask Dr. Mira to kindly leave the meeting. We will connect again around 5:30. We need to change room after the question and answer, so we will connect around 5:30. Perfect. Okay, perfect. Yep, okay, thank you.
Have to take. Yes.
You made in one of the third to last slides a recommendation to keep the drift limits to 1.5%.
Yes.
And I was wondering if that is tied to some level of collapse probability that you've decided is appropriate.
Yes. that recommendation that you see there is, we have defined MCE as being the 2,500 year return period hazard level as per 1170.5, which is 1.8 times of the DBE. And deciding on the acceptable level of collapse probability is beyond my research, but I have just made that recommendation to achieve a collapse probability for MC defined as 1.8 times DBE to be pretty much less than 20%, if that makes sense.
At MCE?
Yes, at MC, but that MC definition is different, for example, to the MC definition in ACE 7. So that should be noted. So based on that equation, if you use that equation for drifts of over 1.5% for MC level, we get collapse probabilities of higher than 20%. I believe it's not acceptable, but that issue of definition of allowable collapse probability is just beyond this topic.
Thanks for the presentation, and it's a clever way to look at collapse, going all the way down to this elastic drift is the key measure that can control it. It takes a huge amount of work to do that.
Yeah, thank you very much. Greg, do you have any questions?
Yeah, I agree with Maxim's statement that having drift as a key design parameter makes a lot of sense, because in the end we've got to have something that an engineer feels comfortable with. And when we come up with, we just had a session on loss, and everyone's got their own way of doing it. And if people are asked to find loss for something, they'll get 20 different answers, and this variation will be big, and you can't measure it. So I think it's really good you've done that. I suppose the big one is at the very beginning you said in LOSD, what you do is you define an acceptable level of loss. How do you define that?
Again, that definition goes beyond the topic of my PhD research. I know it's very controversial how to define the acceptable level of loss. Outside the scope of my research, in my personal opinion, yes, we can actually propose some values for it, and that can be done based on the observations in the society. So the acceptable level of loss in terms of injuries, deaths, and financial losses can be somehow predicted based on the experiences of previous earthquakes in different regions and verifying the implications to the society. It's a very huge topic by itself. There are, as you know, several people in the world working on it, and it's an ongoing research. I don't think I can answer that question better than this at this point, because it's the topic of ongoing research. Yeah.
How did you define collapse for sideway moves? Like they define a certain drift limit or non-convergence. How did you define collapse? Like I know like the fiber can at element level, but how did you define collapse?
Yes, it's a very good question. So sideway. So we are capturing two modes of collapse, sideway as well as the vertical. So sideway mode of collapse is captured when, with a small increase in the intensity of earthquake, you get a huge jump in interstory drifts. And if you draw a curve, an ID curve, you see a sudden abrupt increase in the interstory drift, so your ID curve flattens out. This is how different people capture the sideway mode of collapse. For the vertical mode of collapse, we have identified that when in fact in the analysis is terminated. And to verify that, first of all, a very robust algorithm has been developed in OpenSys. So I've worked almost a year on that algorithm, and I've actually used the previous algorithms developed by others. to make sure that when the analysis is terminated, it's not because of numerical instability, but in fact it is because of actual components and the structure failure. And when I showed a few examples that when the analysis was actually terminated, we went back and saw those fibers and saw that, all right, why this analysis has terminated. And because we were able to explain it at those points. So there were the points that we could see failure in the section. So we became confident that, all right, our analysis has been terminated not due to numerical instability, but due to actual component failure, and not only a single component failure, the component failure that eventually results in the failure of the structure, the ability of the structure to continue carrying the gravity loads.
And they showed that the probabilities for collapse at MCE are quite high, according to your opinion. Are they in the same range for lump plasticity models? Because when usually we look at IDA curve in previous studies, like it takes a lot of scale factors, like very high intensities to cause collapse.
Yeah.
So
yeah.
are these values consistent with seismic collapse, or these are higher because you've considered?
Yes. To answer your question, I refer you to this table. So if this is the collapse probability assessment for the building, which is a well-detailed ductile structure. If we ignore the modeling uncertainties, you can see that at MCE level, the collapse probabilities are still pretty low. And also, note that this MCE is a very large hazard because it is 1.8 times of the DVE. And if we compare these values with, for example, likes of Hasselton research for ductile structures, is very close actually. And so my findings are pretty much matching with their findings. I'm just using a different hazard level.
But
here.
Despite different modeling techniques, your values are consistent with his values.
For ductile structures, yes, but if we use, as soon as we go to higher LSR, then if I go to, for example, this table here, so if I go to this table here, you can see that with higher LSRs over 5, then collapse probability is high. I would say unacceptably high. But if it is well detailed, LSR is 5, the collapse probabilities for well-designed buildings is relatively low for MCE level. And just to give that some perspective, so you can see these pretty low collapse probabilities even at the hazard level, which is 1.8 times DBE for the Redwood building. It is pretty low, but if you go to this interstellar drifts calculated based on New Zealand standard, you can see that the maximum is just 1.2%. And that is why I believe that 2.5% drift at DBE level allowable in New Zealand standard is just too high. And this building is designed for 1.2% drift only, and that's why we get good results for it. So it's good detailing plus low interest store drifts that can save the building. Yes.
I have a few questions. First of all, very good presentation. Thanks for that. So for these designs, did you also check the curvature limits that they are in 3404 along with the drift limits that you checked in 1170?
3404 for a still structure.
Sorry, 311.
311.
Yeah.
Yes. So the curvature limit.
Yeah.
There is are you talking about there is one requirement at the beginning? So first of all, majority of my case study buildings are not complying exactly with 3101. So if I go to this table, I just go back to this table. So these are the case study buildings other than the Red Book. For the Red Book is compliant completely. The only one which is somehow is conforming is the base building. Yes, for this base building it was checked, but again, deliberately, I really pushed the design to maximum possible allowable in the code, because the purpose was if there is some drawback, we can identify it and we can exaggerate it and we can actually show it. So I would say, as a design engineer, majority of engineers in New Zealand, they don't design a building like the base building here in this example. But as a practicing engineer, I have seen several engineers, unfortunately in practice, that they push the buildings to higher drifts because economically they benefit from it. The problem is that we don't have an empirical equation in New Zealand standards to calculate the structure periods. So the more flexible your building becomes, the higher period you get. The higher period means that there are less forces. So you make some mechanical savings in the building. So engineers, they push the buildings to softer, more flexible structures to save materials. And that is very dangerous. I have personally peer reviewed several buildings, seen engineers doing it, and my hands are tied because they're just like complying with the code. They are estimating the structure period based on the code, as there's no empirical equation to calculate, despite the fact that we do have empirical equations in say likes of ASC 7. There's not in New Zealand standard, and the allowable interstory drift at DBE is 2.5%. So yeah, people make the building more flexible, meaning higher period, means less forces to design their components, meaning more risk of collapse.
One of the reasons I asked that question was if you observe, like, just I'm asking as a curious student with no design or consulting experience, that which of those two factors becomes controlling usually, the curvature or the strain limits from 3101 or the design drift limit, usually when you're designing?
It depends. It varies the building to building, but a lot of buildings I have observed that curvature limit is actually governing. But take that with a caution because it's not happening all the time.
Okay, thank you. Another question I have is around the material model that you use, the fiber element model. Mm-hmm. If you did any work around that as part of your work, or if you're aware that if you compare that fiber element model to the plastic lump plasticity model that we have in OpenSea that consider the cyclic degradation, if the two of them, just the degradation factor matches well, or if one considers more?
Yeah, so one example of it you can see in this slide here. What I have observed, as you can probably see in the curves below, is that because generally speaking, LSR is neglected in those studies. So if we take a low LSR, like detail it, as soon as we detail a section with closed space stirrups, with the lump plasticity models, we get very good behavior. The parameters, they become such that we get good, a lot of interstory drift or plastic deflection limit. That pretty well matches with the fiber model if we use low LSR. But as soon as the LSR goes even slightly more, then the difference starts to show off. This is what I observed. If we go to like those lump plasticity models, experimental tests, you can see there is a standard deviation as high as 70%. So I would imagine part of that 70% And you can see in literature that pretty much most of the researchers, they are suggesting 50% uncertainties in structural modeling. That could actually come from the fact that they are ignoring LSR. So in the tests, one section shows good results, and the next section is still conforming. It's not showing very good results. So something's missing here. That could be the point here. This Rajesh has shown that that is the point.
Okay, I think
No, I think it's fine. We can wrap up. But I think as you are working on that field, I think one good thing that you have to remember is currently the design codes only look at anti-buckling as well as confinement properties similarly, right? Whereas research has shown that the confinement, which is the ability of the core concrete to withstand large strain, depends on the amount of stirrups, right? Whereas the anti-buckling performance depends on the arrangement of stirrups. And that is the factor which is missing in all codes, like be it ASC or New Zealand or Japan, right? So now, what the long plasticity, the indication or the instructions to get the calibration parameter for these plastic hinge model is based on ASC 713, that table which looks at, okay, well detailed, not well detailed, shear to flexor ratio and all those things, right? So that is inherently there based on once you have got the spacing very close, then okay, it meets that, ticks off that criteria. But what if your intermediate bar is actually pulled out and you get your buckling within a longer length between 3 stirrups, right? So in that case, actually, your section is as good as, for buckling, it is as good as not having those 2 stirrups, right? So that's why, because the mismatch. So when it is enough stirrup, enough well-arranged stirrup, you get similar performance. But the fiber model, especially using LSR, which is kind of measure of ductile detailing in the truest sense, right? So that is, yeah.
Thank you, Rajesh. I think it's time to wrap up, but before that, join me and congratulate.
Not yet time to congratulate, but thanking him. All right, so.
All the best, Mohammed.
Thank you very much. Very nice to see you.